Hello, and welcome to the OpenBrIM Platform. In our previous video, we learned how to create a bridge skeleton using the OpenBrIM Platform. Now, over the next few minutes, we will demonstrate how to build our superstructure model on top of this created bridge skeleton. Let us begin. First, in the tree view, we navigate to the bearings category under the superstructure category. Bearings are structural elements placed between the bridge superstructure and substructure. Their primary functions include load transfer of vertical and horizontal forces, allowing movement for thermal expansion, deflection, and seismic displacement, and permitting rotation at the girder ends. In this category, you can select the appropriate bearing type and add it to your project. The bearing seat is the concrete or steel surface on which the bearing rests, defining the contact region between the bearing and the substructure. FEA bearing is not a physical bearing, but rather a numerical object representing boundary conditions in the analysis model. It is defined by spring stiffness values for translational degrees of freedom, or rigid constraints for rotational degrees of freedom. Steel-reinforced elastomeric bearing consists of rubber layers with vulcanized steel plates between them, allowing both horizontal movement and end rotation. This is the most common bearing type. Pot bearing is a high-capacity bearing preferred for long-span bridges. It features an elastomer disc compressed inside a steel cylindrical pot, allowing rotation in all directions while carrying high vertical loads. Single roller bearing is a steel bridge bearing with low friction and high load capacity. It permits translation along a single axis through the rolling motion of a single steel cylinder. Sliding plate bearing uses a very low coefficient of friction at the polytetrafluoroethylene and stainless steel interface, enabling free translational movement. It is typically used in combination with other bearing types. For all bearing types, you can override the stiffness values that are automatically computed based on other inputs. If you do not know your bearing type, you can simply use an FEA bearing for the FEA simulation and assign the stiffness values accordingly. For this project, we will also define FEA bearings. Now we click on FEA bearing in the tree view. In the insertion point parameter, we click the three-dot icon button, then select Select. In the interface that opens, we select IP1 and click OK. Now we will define the spring stiffness values and rotational rigidities. Two fundamental approaches are used in structural analysis to define bearing behavior. Rigid constraints assume that the bearing either completely prevents movement or is completely free in the relevant direction. In the fixed state, force and moment transfer occurs, while in the free state, force transfer in that direction is zero. Spring stiffness values, however, recognize that no connection in the real world is perfectly fixed or free, and define an intermediate rigidity behavior. Here, the bearing provides resistance with a certain flexibility proportional to the applied force or moment. For modeling purposes, using realistic stiffness values instead of idealized, fixed-free conditions is recommended. For example, if the substructure is not modeled and only the bearings are included, assuming fully fixed behavior will overestimate the actual system stiffness. When the substructure is modeled, using fixed conditions becomes less critical, since the substructure itself reduces the overall stiffness in the direction of interest. Now we click the three-dot icon button in the TY parameter and set it to fixed. Then we click on the TZ parameter and set the value to 10,000. We leave the other parameters at their default values. For the second FEA bearing definition, we click the three-dot icon button in the insertion point parameter again and select Select. In the interface that opens, we select IP2 and click OK. We select the insertion points of the two defined FEA bearing objects. We hold the blue dot at the bottom right of the selected parameters with the mouse and drag it down for the 16 insertion points defined in the project, similar to Excel. Now we click the three-dot icon button in the TX parameter of BF5 FEA bearing and set it to fixed. Then we hold the dot at the bottom right of the row and drag it down to BF8, similar to Excel. We leave the TY, TZ, RX, RY, and RZ parameters of the FEA bearings in their final state. We leave the bearing rotation parameter at the default setting of 0 degrees. On curved bridges, deck guidance can be either tangential or radial. Tangential alignment, generally preferred for structures with constant curvature, is achieved with a bearing rotation of 0 degrees, whereas radial alignment requires non-zero rotation values. Accurate input of these values is essential, as incorrect rotations can lead to discrepancies in forces reported in the local bearing axes. In addition to this parameter, we will also leave the transfer forces to substructure parameters as no for now. In later stages of the project, when we complete the substructure modeling process, we will set this parameter to yes for the necessary bearings. If the user opts to connect to the substructure, a two-node spring is created between the pier cap and the girder. Conversely, selecting No generates a single-node spring with defined fixities, which allows the user to analyze and design the superstructure independently of the substructure. If you would like to modify the FEA bearings graphically, you can switch to the Graphical Settings category and make adjustments. The gap parameters define an initial clearance that must be overcome before the bearing support becomes active. This models conditions where bearings may have initial clearance before engaging. In our project, we will leave the gap parameters at 0. We have defined our FEA bearings. Now we navigate to the plate girder object under the steel girders category in the tree view. We will create girder objects using the girder layouts we created previously. We click the three-dot icon button in the girder layout parameter and set the GL1 layout. You can define the girder dimensions numerically if you have a single section, or define them at different locations along the girder if the section varies. In our project, we will define them at different locations along the girder. After we click the three-dot icon button in the top flange width parameter and select Edit Spreadsheet. In the interface that opens, we set the start station value to 0 feet and the length value to 113.3 feet. Then we set the top flange width value to 15 inches. Then we set the length values in sequence to 84, 123, 84, and 113.3 feet. Then we set the width values in sequence to 21, 15, 21, and 15 inches, and click the back button. After the girder is created, we click the +Z direction for plan view in the direction indicator at the bottom right and examine the dimension change in 3D view. It is also possible to modify dimensions collectively, enabling us to set the measurements efficiently. First, in the data spreadsheet, select the top flange thickness and web depth dimensions. Next, click the three-dot icon button and choose Edit. The length measurements are then entered sequentially as 113.3, 22.9, 40, 21.1, 123, 21.1, 40, 22.9, and 113.3 feet. The top flange thickness dimensions are set sequentially to 1, 1.25, 2.5, 1.25, 1, 1.25, 2.5, 1.25, and 1 inch. Finally, the web depth dimension is set to 84 inches. Then, hold the blue dot at the bottom right corner of the parameter, drag it to the last station, and click the back button. For other dimensions, we copy and paste the data from the Excel link provided in the video description. We do not change the value we brought from Excel for the haunch thickness parameter. The haunch thickness, measured from the deck bottom to the top flange bottom, can be customized with non-prismatic variations and multiple values using the Edit Spreadsheet or Variation options. Similarly, we do not change the additional haunch width value. The additional haunch width extends from both sides of the top flange, influencing automatic haunch load calculations along with haunch thickness, while hybrid girders support different materials for the top flange, bottom flange, and web, including station-dependent steel variations. For top flange material, we click the three-dot icon button in the parameter and click Import Material. In the interface that opens, we select Steel Material Database US for database and A709-50 material for asset. Then select Import. Then for the other materials, we hold the blue dot at the bottom right of the parameters with the mouse and drag it to the right up to bottom flange material. Then drag it down to the last girder. The transfer girder parameter specifies whether the selected girder functions as a transfer girder. If set to yes, it indicates that a kicker girder connects to the main girder rather than being supported directly between abutments or piers. This setting influences the FEA meshing behavior of the deck girder system. When enabled, the mesh configuration under the deck object must also be updated, as the default grid mesh algorithm may not perform well for complex geometries. For this example, using the frontal Delaunay for quads meshing algorithm is recommended. In our project, we will leave this parameter as no. The connecting girder parameter appears as not applicable because the transfer girder parameter is set to no. For this parameter to become active, the transverse girder parameter must be set to yes. This parameter indicates whether the selected girder is connected to another girder for meshing purposes. It helps adjust the mesh generation along the deck where girders intersect or share connectivity. This parameter does not affect load transfer or continuity behavior. FEA-related settings can be modified using the parameters within the FEA settings category. The mesh size parameter specifies the maximum distance between nodes in the longitudinal direction, as defined by the longitudinal mesh size. In most cases, a smaller mesh size may be applied, depending on the locations of bracing, deck pouring or removal, or changes in section geometry. The number of result extraction stations parameter relates solely to the configuration of result extraction segments used for viewing FEA composite results in either the spreadsheet or the FEA interface. It does not influence standard finite element analysis outputs, including member end forces, nodal displacements, and nodal reactions. For girder code verification, the precise code check stations are used in the evaluation of FEA composite results. By default, results for FE composite elements are generated at the standard stations. If results are required at a specific additional station, the additional result extraction station parameter can be used. This does not affect the overall FEA. Only the composite element forces and composite element stresses are calculated according to the inputs specified in the additional result extraction station parameter. Now, let us demonstrate how the additional result extraction station parameter works with an example. First, click the Analysis button at the top left. After the analysis is complete, click the FEA category. Under the Results category, click Composite Element Forces. The analysis results for specific positions will be displayed on the screen. Next, click the Steel Eye Girder Bridge button. Then, in the tree view, select the Plate Girder object. Click the FEA Settings category. Following this, click the three-dot icon in the Additional Result Extraction Station parameter and select Edit. Set the station values to 2 feet and 5 feet. Then, click the Back button. Since this action does not alter the analysis results, continue the checks using Previous Results. Click the FEA button again. And as before, click Composite Element Forces. Check the position parameter. The analysis results for the added stations at 2 feet and 5 feet are now displayed in the spreadsheet. Finally, click the Steel Eye Girder Bridge button again and remove the additional stations that were added. We have completed our girder definitions. Now to define stiffeners, we click on the Transverse Stiffener object under the Stiffeners category in the tree view. Additional stiffeners, beyond those located at cross-frame positions, can be incorporated using this component. Both the FEM and 3D model can be generated based on the input parameters specified in this section. We click the three-dot icon button in the girder parameter and select the G1 girder. We set the station value to 130.24 feet. A positive skew value rotates the stiffener in a clockwise direction, while a negative skew value rotates it in a counterclockwise direction. We do not touch the skew angle parameter, which remains at the default value of 0, as there is no skew angle in the project. The side of web parameter defines the placement of the stiffener relative to the web when viewing stations along the PGL, allowing selection of the right side, left side, or both sides of the web. For material definition, the Steel Material Database, US, is imported as previously described, and a 709 grade 50W is selected for the asset. To view the created stiffener in 3D view, we click the three-dot icon button on any parameter in the stiffener object and select Select Object. Then we click the Zoom Extents button at the top right. We will leave the other parameters at their defaults in our project, but if you want to change the dimensions, you can do so with the parameters in the Dimensions and 3D Detailing categories. For FEM, the stiffener finite element is a connection element positioned between the top flange and bottom flange nodes. Choose Yes if you wish to generate this element. If this parameter is set to Yes, the stiffness and weight loads of the stiffeners will be applied and considered in the FEA, regardless of the definitions made in the girder and bracing partial or girder and bracing complete sections under superstructure construction within the construction category. We have completed the transverse stiffener definition. Now in 3D view, you can double-click anywhere with the mouse, then click the Zoom Extents button to return to the general view of the project. Now we will define a splice for our project. The bolted field splice has no direct impact on the finite element model and is only used for design and 3D visualization purposes. Before moving on to object definition, let us make the bolt property definition required for the splice. To define bolt property, we click on the bolt property object under the property category in the tree view. For flange bolts, we click the three-dot icon button in the diameter parameter and set the value to 0.875. Then we set the nut diameter value to 1 inch. To distinguish the bolt name, we set the name flange bolt. For web bolt, we set the diameter of the nut parameter to 1.4375. Then we click on the bolted field splice object in the tree view. We click the three-dot icon button in the girder parameter and set the G1 girder. We set the station value to 118.7 feet. Then we set the gap between girders value to 0 inches. We examine the issue provided in our project. The issue indicates that there are no bolt definitions for the object. We move to the bolts category and set the web bolt property and flange bolt property that we defined earlier for bolt property. After this process, we return to the girder category. We leave the dimension parameters for this object in their default states. If you would like to examine in detail what each of the dimension parameters means, you can review the documentation linked in the video description. Now we click the three-dot icon button on any parameter and select Select Object. Then, when we click the Zoom Extents button, we view the splice object in 3D view. Now let us model the other splice objects. We copy the data from the splice page in the Excel file linked in the video description and paste it into the data spreadsheet. We have defined the splice objects in our project. Now we will define the shear stud object, which is another connection object. Shear studs do not directly affect the finite element model and are used only for design and 3D visualization purposes. We click on the shear stud object in the tree view. We click the three-dot icon button in the girder parameter and set the G1 girder. Then we set the start station parameter to 1.975 feet and the end station parameter to 73 feet. We leave the shear stud dimension values at their default values. If you would like to examine the parameters in detail, you can review the linked documentation again. Now we go to the shear stud category. We click the three-dot icon button in the Show Studs parameter and click the Yes option. Then we activate the detailing button at the top of the screen. The shear stud object has become viewable in 3D view. Now we can close the detailing and add the other shear stud objects to our project. We copy the table on the shear stud page in the previously linked Excel file and paste it into the data spreadsheet. We have defined the shear stud objects. Now we will define the crossframe objects. 7 types of crossframes can be modeled for steel girder bridges. In this project, we will model crossframes as K-top and X-type examples. You can review other crossframe types in the documentation. We click on the crossframe K-top object in the tree view. We click the 3-dot icon button in the Girders parameter and select Pick. We select the G1 and G2 girders in 3D view. We examine the issue that appears. To eliminate the issue, we click on the section category. We click the 3-dot icon button in the top chord section parameter. In the interface that opens, we click Import Section. In the section database interface, we select AISC steel shape for database, L type for category, and AISC-L 8x8 by 3/4 for shape. Then we click Import. Then we hold the blue dot at the bottom right of the parameter with the mouse and drag it to the diagonal chord section. Then we return to the location category. Enter the station along the PGL. When dealing with curved girder bridges, collecting distance along the girder length can lead to different inputs for the right and left girder that are connected by crossframes, causing ambiguity. Therefore, collecting the station along the PGL is a more reliable solution to avoid such issues. Furthermore, since crossframes are typically continuous in the transverse direction, entering the same station for all crossframes ensures that their locations are consistent between each girder. The same principle can be applied for skewed crossframes. Inaccurate finite element models and disconnected nodes or elements in the crossframe can occur if the entered station values are not greater than or equal to the girder start station or less than or equal to the girder end station. This can cause stability issues in the finite element model. To ensure correct station input, users should select the start or end options from the station input. This approach is especially recommended for crossframes located at the beginning or end of girders. For this reason, we click the 3-dot icon button in the station parameter and select Start. To define the other crossframes, we copy the parameters on the crossframe K-top page in Excel and paste them into the spreadsheet. We have completed the crossframe K-top objects. Now we click on the crossframe X object in the tree view. Then we click the 3-dot icon button in the Girders parameter and select Pick. We select the G1 and G2 girders in 3D view. To remove the issue, we click on the Sections category. The chord parameters here are used to determine whether top, bottom, or diagonal chords are present. If defined as yes, a section can be assigned to the top chord of the crossframe using the top chord section parameter. Otherwise, the top chord section parameter will be not applicable. Now we click the 3-dot icon button in the top chord section parameter and set the section we defined earlier. Then we hold the blue dot at the bottom right of the parameter with the mouse and drag it to the diagonal chord section. The chord orientation angles in this category specify an angle for the chord to rotate around its longitudinal axis. We will leave these parameters in their default state. We return to the location category. Skew angle parameter defines that a positive skew value rotates the crossframe in a clockwise direction, while a negative skew value rotates it in a counterclockwise direction. It is important to remember that the crossframes are positioned at the specified station along a line perpendicular to the PGL, which is then rotated according to the entered skew value. Since we do not have a skew angle in our model, we will leave this parameter at 0. The working principle of the station parameter is identical to that of the crossframe K-top object. For this object, the station parameter is set to 20 feet. If the has-middle gusset plate parameter is set to yes, a gusset plate will be generated at the overlapping section of the X. A node will be created at the junction of the two diagonals if this parameter is defined with the yes option. To disable this, click the 3-dot icon in this parameter and select the no option. The cord flipping side can be specified using this parameter. We leave this parameter in its default state. To define the other cross frames, we copy the parameters on the crossframe X page in Excel and paste them into the spreadsheet. We have completed the crossframe X objects. Now we click on the cross-section object located in the deck category in the tree view. The cross-section object allows you to define the section in which the deck will be created. Next, we click the three-dot icon button in the Use Custom Alignments for Deck Edges parameter. This parameter allows you to reference a custom alignment instead of the main alignment when defining deck cross-sections, provided that a custom alignment already exists in the project. In the interface that opens, we set the value to Yes. When creating the deck cross-section, the custom alignments that define the left and right boundaries of the deck must already be defined in the project. While defining these alignments, a vertical profile is not required for the cross-section. Next, we click the three-dot icon button in the Alignment Left Edge of Deck parameter and set it to Alignment 2. Then we click the three-dot icon button in the Alignment Right Edge of Deck parameter and set it to Alignment 3. After this process, we set the mid-thickness parameter to 9 inches. The mid-thickness of the concrete deck, excluding the overhang part, is utilized as the thickness of the deck shell elements in finite element analysis. The left overhang thickness and right overhang thickness parameters are maintained at their default values. These parameters define the maximum thickness of the overhang and influence the thickness of the deck shell element in the overhang region. The taper parameter is incorporated into the deck component data. Additionally, if the deck is constructed using automatic haunch load computation, any additional load will be adjusted, either added or removed, based on the thickness and taper parameters of the deck overhang. We have defined the deck cross-section. Now we can create the deck. We click on the concrete deck object in the tree view. We click the three-dot icon button in the cross-section parameter, then click the Edit button. Cross-section location is used to determine the support lines that will be used to define section locations. We click the three-dot icon button in the parameter and set the Abutment 1 support line. We set the section we defined in the cross-section parameter. The variation parameter offers the user the choice of how to join cross-sections. Before making this choice, let us try to show the working principle with a few visuals. The first visual shows the situation when the variation choice is none. The second visual shows the image created after this choice is set to linear. In our last visual, the image is created if variation parabola is chosen. For this project, we make this choice as linear. We click the three-dot icon button in the parameter and set linear. To generate a deck, at least 2 row definitions must be made. The required definitions are the support line and its cross-section at the start station, as well as the support line and its cross-section at the end station. However, the offset from support line parameter should not be used for either of these definitions, as it is not the correct parameter for extending the deck before the start station or after the end station. Instead, use the Initial Cantilever Length and End Cantilever Length parameters on the 3D Settings tab. We click the three-dot icon button in the cross-section location parameter and set the Abutment 2 line, which is the support line at the end of the bridge. Then we click the Back button. To create the 3D geometry for the haunch and finite element mesh of the deck, input for the girder is required. To ensure accurate extraction of composite forces, the library component will generate a minimum of 2 shell elements between 2 girders. We click the three-dot icon button in the Girders parameter and select Pick. Then we select the girders we created in 3D view. In the overhang regions, users can choose whether or not to include taper by selecting Yes or No, as shown in the figure below. This input will impact the haunch load computation. We leave the taper parameter as default. Overhang bottom flat parameter is activated only when the taper input is set to No. Its purpose is to explicitly flatten the bottom surface of the concrete deck overhangs. Otherwise, the overhang bottom aligns with the existing cross-slope angle. We click the three-dot icon button in the Material parameter, then select Import Material. In the interface that opens, we select Concrete Material for Database, US AASHTO for Category, and finally 4 kips per square inch for Asset. Then we click the Import button. The deck object has been created. Now we return to the deck cross-section object. We click the three-dot icon button in the Use Custom Alignments for Deck Edges parameter and set the value to No. Next, we set the PGL to left edge and PGL to right edge parameters to 20.25 feet. With this method, we also demonstrate how the deck object can be defined using the main alignment. Finally, we return to the deck object in order to define the reinforcement. We will create deck reinforcement data for use in the code check process. We click the three-dot icon button in the deck reinforcement data parameter, then click Edit. We set the starting station as 0 feet for start station. We set the end station parameter to 530 feet as well. The point to note here is that if there is a skew at the deck start and end stations, the deck reinforcement stations must be calculated taking the skew into account. Station values should be offset relative to the deck edges, as shown in the picture I showed. Otherwise, the code checks behind and ahead of these stations, red line in the reference picture, will not have deck reinforcement data. We click the three-dot icon button in the deck rebar material parameter and select Import. In the interface that opens, we select Steel Material Database US for Database, Reinforcement Steel for Category, and finally, a 615-60 for Asset. Then we click Import. We set the top and bottom layer rebar spacing to 5 inches. To set the top layer longitudinal rebar, we click the three-dot icon button and select Import. In the interface that opens, we select Category ASTMA 615 and Asset number 8, then click Import. For the bottom layer, we import number 6 using the same method. We leave the Clear Cover and Concrete Creep Adjustment Factor parameters unchanged at their default values. The FEA and 3D settings parameters will be left as default. However, we find it beneficial to provide additional information about a few parameters. In the FEA category, the Expansion Joint End Releases parameter specifies that the deck mesh will generate 2 nodes at the same location for the specified station and connect them with springs. Spring stiffness will be assigned based on the values entered by the user in respective directions. This is another way to model discontinuous decks, expansion joints, or even hinges. And finally, the Mesh Algorithm parameter controls the algorithm used to generate the finite element mesh for the deck. The default option is Grid Mesh, which creates a structured grid-based mesh aligned with the girder lines and includes mid-references between girders. Other algorithms use advanced meshing strategies that may be beneficial for complex geometries or specific analysis requirements. Now, let us demonstrate how the other algorithm options affect the deck FEA model. First, open the previously prepared FEA model. Click the three-dot icon button in the Mesh Algorithm parameter and choose Select. In the interface that appears, select Mesh Adapt and click OK. Repeat the same process for the Automatic option. The changes made by the Automatic option in the FEA model are now displayed on the screen. Now, let us perform the same process for the initial Mesh Only option. Next, repeat the same process for the Delaunay option. If you are using any nonlinear variation for deck cross-sections or alignment for deck edges, the preferred algorithm is Frontal Delaunay for quads. Let us repeat the process for this algorithm option. Finally, repeat the process for the quasi-structured quad option. And now, let us return to our main model. We have completed creating the deck object. Now we click on the barrier object under the Superstructure Attachments category in the tree view. We click the three-dot icon button in the section parameter. To create a custom section for the barrier, the section editor can be used. The weight of the barrier will be computed based on the area of the assigned section. When applying wind loads, the depth of the barrier is important. Users can utilize the concrete material without changing the stiffness value and construct the barrier under the superstructure attachment construction, with options stiffness equals no and weight factor equals 1. In the interface that opens, we select Import Section. In the interface that opens, we select Barrier Section for Database, F-Shape Barrier for Category, and finally, F-Shape for Shape. In this interface, you can change the dimension parameters before importing the section. From these parameters, we set the chamfered edge parameter to 0 inches, leave the others as default, and click Import. We leave the orientation parameter at its default value. The orientation of the barrier should be set as left for the barriers placed on the left end of the deck, and right for those placed on the right end, to rotate the barrier section accordingly. We click the three-dot icon button in the deck parameter and set the deck object we defined. We leave the parameters related to start station and end station at their default values. If you want the barrier start or end station to be automatically assigned as the deck start or end, the deck start option should be selected in the option choices. If your barrier starts at a different location along the PGL, you can choose the input option. The transverse station is defined relative to the PGL, where the PGL location is 0. When the user clicks on the three-dot icon button, the Set to Left or Right options appear, which enable the barrier to be positioned quickly at the exterior end of the deck. For the barrier we defined, we click the three-dot icon button in the Start and End Transverse Location parameters and set the Left option. For the other barrier, we click the three-dot icon button in the Orientation parameter and click the Right option. Then we click the three-dot icon button in the Start Transverse Location and End Transverse Location parameters and set the Right option. We have completed the barrier objects. Finally, we click on the Roadway object in the tree view. The roadway definition is used for influence surface-based live load analysis. Based on the roadway definition, an influence surface path is generated and influence coefficients are computed. OpenBrIM influence surface-based live load analysis automatically places lanes at the transverse locations, so the only important parameter to define is the extent of the roadway. We click the three-dot icon button in the bridge parameter and set the previously created bridge alignment object. Then we click the three-dot icon button in the roadway dimensions parameter and select Edit. We set the station value to 0 feet. Then we set the right width and left width parameters to 18 feet. We have set the roadway start parameters. Now we set the end station to 530 feet and click the back button. With the roadway, we have completed defining the superstructure objects in our project.